Imagine, if you will, a catastrophe so vast, so just unfathomably violent, that it literally reshapes the topography of the Earth.
Right.
It erases early human settlements in an instant, and it fundamentally alters the atmospheric chemistry
Right.
across an entire hemisphere.
Yeah, it's hard to even wrap your head around.
It really is. And there are no scrolls, right? No stone tablets, no terrified eyewitness accounts passed down through history, just absolute silence. It's the kind of event that, if it happened today, it would permanently alter the trajectory of human civilization. But because it happened before the dawn of recorded history, it's essentially a ghost.
A ghost that left a colossal physical footprint, though, provided you know exactly where to look and, more importantly, how to read the terrain.
Right.
We are talking about the ultimate geological cold case here. It's an investigation that relies entirely on environmental fingerprints rather than human memory.
Exactly. So for everyone listening, think of yourself as the third investigator in the room with us today. We're taking a deep dive and traveling to the Kamchatka Peninsula out in the Russian Far East.
A beautiful but highly volatile place.
Oh, absolutely. And our mission today is to reconstruct a massive volcanic event that occurred roughly 8,400 to 8,500 years ago.
Or, if you're deep into the radiocarbon dating world, you'll often hear this referred to as 7,600 years before present.
Right, 7,600 BP. We're specifically investigating the Kuril Lake caldera and the eruption that created what geologists call the K.O. tephra layer. And we are pulling from a massive stack of source material to do this.
We really are. We've got geological surveys from the Russian Far East.
Yep.
We have deep sea core data pulled from the frigid waters of the Sea of Okhotsk. There are ice core records drilled straight out of Greenland, and some highly detailed archaeological data from the Kuril Islands.
It's a lot of puzzle pieces, and our goal is to reconstruct this event purely from those scattered environmental clues. We really need to carefully separate the hard geochemical facts from the speculative apocalyptic myths that usually surround these massive volcanic eruptions.
Which is so important. We are dealing with objective, verifiable data here. We're piecing together a timeline from literal microscopic shards of glass and chemical anomalies buried deep in the ice.
So the sheer scale of what we're talking about is it's almost hard to visualize, right? So I think we have to start by understanding the violence of where it all began.
Yeah, let's start at ground zero.
If you look at the last 12,000 years of Earth's history, the Holocene epoch, which is basically the window of time where humans have been building societies, this one chunk of real estate in Kamchatka is responsible for an absurd amount of the planet's largest explosions.
Kamchatka is, quite literally, the definition of a geologic powder keg. It sits on the northwestern edge of the Pacific Ring of Fire, and that's where the Pacific Plate is actively subducting or diving under the Okhotsk Plate.
Grinding right underneath it.
Exactly. And this tectonic friction creates an incredibly volatile volcanic region. Just to put some hard numbers on it for you, during the entire Holocene, there were 6 eruptions in Kamchatka that produced tephra volumes greater than 10 cubic kilometers.
Which is already massive.
Oh, it's huge. And 4 of those 6 occurred entirely in southern Kamchatka.
And sitting right there in the southern tip is the Kuril Lake caldera. Now, the eruption that formed this specific caldera, the K.O. eruption, achieved a volcanic explosivity index, or a VEI, of 7.
Yeah, a VEI 7 is no joke. The VEI scale is logarithmic, much like the Richter scale is for earthquakes.
So it jumps up exponentially.
Right. It measures the explosiveness of an eruption based on the volume of material ejected, the height of the eruption cloud, and various qualitative observations. Now, the scale maxes out at 8, which is completely reserved for supervolcanoes, like Yellowstone.
Okay, so 8 is the literal top of the chart.
Yes. So a VEI of 7 puts the Kuril Lake eruption in ultra-rare territory. To give you a comparison, it makes it comparable to the infamous 1815 eruption of Mount Tambora in Indonesia.
Which is famous for causing the year without a summer.
Exactly, the one that caused widespread crop failures across North America and Europe. The K.O. eruption firmly ranks among the Earth's absolute largest explosive events of the last 12,000 years.
The volumetrics we're looking at in the source data are they're staggering. We are talking about 140 to 170 cubic kilometers of erupted tephra.
It's an astronomical amount of material.
I really want to pause on that for a second because 150 cubic kilometers of material is practically impossible to visualize.
Yeah.
If you took that much rock and ash, you could bury an entire major city under a mountain of debris several miles high.
Yeah, miles high.
It is an incomprehensible volume of solid earth, instantly converted into ash, pumice, and gas and violently ejected into the atmosphere.
And when geologists look closely at the proximal deposits, meaning the layers of rock and ash right next to the volcano itself, they don't just see a single pile of debris.
They see a story, right?
Yes, they see a minute-by-minute timeline of the mountain's destruction. The stratigraphy, the layering of the rock reveals 3 distinct, quite frankly, horrifying eruptive phases.
It's incredible how the Earth literally writes its own autopsy report.
Yeah.
Let's look at phase 1. The sources describe this as I want to make sure I say this right, the initial Frito-Plinian deposit.
You nailed it, Frito-Plinian.
Awesome. So if there was already a proto-lake sitting on top of this magma chamber, what happens when those two meet? Because I can't imagine water and superheated liquid rock mix quietly.
Oh, they absolutely do not. Frito-Plinian refers to an eruption where ascending magma interacts directly with a significant body of external water.
Like a lake or an ocean?
Right. In this case, it was the proto-lake sitting right on top. The magma was likely pushing up through the crust at temperatures exceeding, 800 or 900 degrees Celsius.
Yeah.
So when it breached the surface and hit that lake water, the thermodynamic reaction was instantaneous and violently explosive.
Think about it like a massive blazing grease fire in a kitchen, right?
It's a great analogy.
The absolute worst thing you can do is throw a bucket of water on it. The water doesn't put the fire out at all. It instantly flashes into steam.
Exactly.
And since steam takes up roughly 1,700 times more volume than liquid water, that massive instantaneous expansion just shreds the burning grease and throws it into the air as a huge fireball.
That is essentially what happened here, but on a massive geological scale. The magma hit the proto-lake, the water flashed to steam, and that sudden steam expansion shattered the molten rock into unimaginably fine microscopic glass shrapnel.
Just instant pulverized glass.
Right. And that intense fragmentation mechanism is crucial for understanding why this ash traveled so far later on. It generated an enormous volume of very fine-grained material, and that violent water-magma interaction basically set the stage for phase 2, which is the Plinian fall deposit.
Because the lake is just gone at this point.
Completely. At this point, the lake water has likely been entirely vaporized or blasted away, clearing the throat of the volcano.
Which opens the door for that classic terrifying volcanic image, a Plinian column.
Yep, exactly.
We're talking about a massive, continuous, towering jet of ash, toxic gas, and pumice shooting straight up into the stratosphere.
These columns are immense. They can reach 30 to 40 kilometers into the sky.
That's way higher than commercial airplanes fly.
Oh, much higher.
Yeah.
The sheer thermal energy and gas pressure driving the magma upward are fighting against gravity and the surrounding atmospheric pressure. And as long as the upward thrust from the volcano is stronger, the column holds.
Wow.
It darkens the sky, it creates its own intense weather systems, complete with volcanic lightning, by the way, and it rains debris over a massive area.
But gravity always wins eventually, right?
It always does.
The thermal thrust starts to wane, or the vent widens so much that the pressure drops. And that leads to phase 3, which, honestly, from reading the sources, sounds like the most destructive part of the entire event on a local level.
Yep. Phase 3 is the ignimbrite sheet. When that towering 30-kilometer-high Plinian column loses its upward momentum, all of that dense, superheated rock, the ash, the gas, it has nowhere to go but down.
Right.
It collapses back onto the landscape, creating a voluminous, ground-hugging, pyroclastic flow. And geologists call the resulting rock deposit from that flow an ignimbrite.
You know, pyroclastic flows are so often misunderstood in popular media. People picture like a slow-moving river of red lava that you can just outrun if you jog fast enough.
Oh, not at all. That's a huge misconception. A pyroclastic flow is a highly fluid avalanche of hot gas and solid volcanic matter.
Yeah.
It behaves way more like a dense boiling liquid than a solid rockfall. It moves at hurricane speeds, easily exceeding 100 kilometers per hour, and the internal temperatures can instantly incinerate anything in its path.
That is terrifying.
It really is. And what stands out in the geological record of the K.O. eruption is the sheer reach and depth of this flow. This boiling avalanche extended over 50 kilometers from the source volcano.
50 kilometers.
Yes. It flowed relentlessly all the way to the Sea of Okhotsk on the west and the Pacific Ocean on the east.
It literally paved the landscape with liquid fire. The courses mentioned that it filled deep, ancient river valleys with hundreds of meters of this boiling rock. It just permanently obliterated the local topography.
Erased it completely.
Rivers that had carved paths for millennia were simply gone, filled to the brim with volcanic glass and pumice.
Yeah. And the sequence of these 3 layers, You know, the initial steam-driven water explosion, the stratospheric Plinian column, and the final ground-hugging avalanche, it records the exact sequence of the mountain basically dying.
Because it empties out underneath, right?
Precisely. When you eject 150 cubic kilometers of magma from beneath the Earth, you leave a massive void underground. The structural integrity of the mountain completely fails. The entire edifice collapses in on itself, and that forms the massive bowl-shaped depression we now know as Kuril Lake.
It's just a textbook example of caldera formation preserved perfectly in the rock. But a VEI-7 eruption doesn't just destroy its own zip code. To understand the true footprint of this event, we have to trace that ash.
And that takes us on quite a journey.
It does. It takes us up to 1,700 kilometers northwest, across the Sea of Okhotsk, into the incredibly remote, freezing lakes of northeastern Siberia.
This is where the story shifts from brutal volcanology to high-precision forensic science. For years, paleobotanists had been out there studying the climate history of the Magadan and Upper Kolyma regions in Siberia.
Looking at old plant life and stuff.
Exactly. They were drilling sediment cores out of the bottom of these remote icy lakes, just trying to understand ancient plant life and climate shifts. But in the process, they kept hitting this distinct, thick, white ash layer.
And they called it the Eruption tephra, right?
Well,
naming it after Eruption 4 Lake, which kind of became the primary reference site for studying this mystery ash.
yeah, the Eruption tephra.
But finding the ash is one thing. Figuring out exactly when it fell is an absolute nightmare in that part of the world.
Oh, it's a huge headache. Dating geological events in high northern latitudes presents very specific, highly frustrating challenges for researchers.
Why is that?
Well, the primary tool we use for this era is radiocarbon dating, which measures the decay of carbon-14 in organic material. To get a date, you essentially need dead plants or animals.
You need carbon.
Right. But these frigid, high-altitude Siberian lakes are incredibly organic poor. There just isn't a lot of life growing and dying in them.
Which means scientists can't just, pick out a nice fat leaf from the mud. They often have to rely on what they call bulk samples. But wait, if they're just grabbing a handful of lake mud and hoping there's enough microscopic organic dust in there to test, aren't they basically grabbing a century's worth of time in one handful?
Pretty much.
How do you date a specific Tuesday, 8,500 years ago, with a bulk sample?
You generally can't, and that is the first major problem. In a slow sedimentation lake, 1 centimeter of mud might represent 100 or even 200 years of accumulation. So if you date that entire chunk, you get a smeared average age, which completely ruins precision needed to match it to a specific volcanic eruption. But the second, even more insidious problem in permafrost environments is the issue of old carbon.
Oh, right. I found this concept fascinating when reading the sources. The landscape essentially holds on to time and releases it entirely out of order.
That's a really great way to put it. Imagine a piece of wood, or perhaps some peat, that died and froze into the permafrost 10,000 years ago.
Okay, so it's frozen solid.
Right. It sits there, perfectly preserved in the ice freezer, completely disconnected from the active carbon cycle. Then, 2,000 years later, the climate warms slightly, the permafrost degrades, and a stream washes that ancient piece of wood right into our lake.
Oh, I see.
And it settles into the mud right next to our mystery white ash layer.
So if a researcher pulls up that core and dates that piece of wood, the machine is going to tell them the wood is 10,000 years old. So they'll naturally assume the ash layer next to it is also 10,000 years old. But the ash actually fell thousands of years after the wood died. It completely skews the timeline, making the sediment appear artificially older than it truly is.
And that old carbon effect plagued the study of the Eruption tephra for a long time. They had dates bouncing all over the timeline. To crack the mystery, researchers knew they couldn't rely on bulk mud. They needed a pristine, undisturbed sample that clearly belonged to the exact time the ash fell.
And they finally found it, right? In a sediment core pulled from a loot lake.
Yes. It was a rare, exceptionally well-preserved plant macrofossil. Specifically, they found a delicate larch twig with the pine cone still attached, sitting immediately directly below the white ash layer.
Just sitting there waiting to be found.
The preservation of a delicate structure like a twig with an attached cone strongly implies it wasn't washed in from ancient permafrost by a violent stream.
Because it would have been broken apart.
Exactly. It likely fell from a tree near the lakeshore, sank to the bottom, and was almost immediately buried by the settling volcanic ash, sealing it perfectly in time.
It's just an incredible stroke of luck. That single fragile twig, buried in freezing mud for 8.5 millennia, basically becomes the Rosetta Stone for dating a cataclysm.
It really was the key.
Because it was perfectly preserved right under the ash, it gave them a highly precise, reliable radiocarbon date. It proved the ash fell roughly 8,400 to 8,500 years ago. But having a date still doesn't tell you the address of the volcano.
No, it doesn't. To definitively link this mystery Siberian ash to the Kuril Lake KO eruption 1,700 kilometers away, the timeline wasn't enough. There are other volcanoes in the world. They had to prove the Eruption tephra and the KO tephra were physically and chemically one and the same.
They needed a fingerprint.
Right. They had to use geochemical fingerprinting.
Now, the sources mention that this ash is rhyolitic, meaning it has a high silica content. And under a microscope, it looks like these flat, plate-like glass shards and highly vesicular pieces of pumice.
Yes, very distinct physical characteristics.
But this is where the science gets really dense, and I think we need to break it down for everyone listening. Isn't all melted rock deep inside the Earth fundamentally similar? Like, how does analyzing chemicals act as a unique, unforgeable barcode for a single eruption?
It's a great question, and it fundamentally comes down to how magma is created and stored. Magma is not just a uniform, homogeneous soup of melted rock slowly churning at the center of the Earth.
Okay.
Its chemical composition varies wildly depending on the thermodynamic conditions of how it was stored in the upper crust, how long it sat there, and the specific tectonic rock it originally melted from. Every single magma chamber has a unique life story.
So every volcano, and even specific eruptions from the same volcano, has a distinct chemical flavor based on its life history.
Precisely. And to find that exact flavor, geologists use a highly advanced technique called electron probe microanalysis, or EPMA.
So wait, you're taking a tiny shard of glass, maybe 10 or 20 microns, across, which is, what, smaller than the width of a human hair?
Much smaller.
And you're firing a focused beam of electrons at it.
That's right. When that electron beam hits the glass shard, it excites the atoms within the glass, causing them to emit X-rays.
Okay, I'm with you.
Every single element on the periodic table emits a characteristic, completely unique X-ray wavelength when it's struck like that. So by measuring those X-rays, the machine can tell you the exact elemental recipe of that tiny shard of glass down to fractions of a percent.
That is wild.
It is. And for identifying Kamchatka volcanoes specifically, geochemists rely on plotting two major elements against each other. Silica, which is silicon dioxide, and potassium oxide. This specific combination is the gold standard for identification in this region.
Let's unpack why those two specific elements are the keys to the lock. Why potassium and silica?
They are crucial because they tell us two entirely different things about the magma's history.
Okay, let's start with potassium.
Potassium is what geologists call an incompatible element. As a magma chamber slowly cools deep underground over thousands of years, minerals begin to crystallize and turn solid. Elements like iron and magnesium fit perfectly into the tight crystal lattices of these early forming minerals.
Right.
But the potassium ion is physically very large. It doesn't fit into the crystal structures of those solidifying rocks.
It's like trying to force a square peg into a round hole while the rock is freezing.
Exactly.
So where does the potassium go if it can't fit into the rock?
It gets continuously rejected by the forming crystals, so it stays behind in the remaining liquid melt. Because of this, the final concentration of potassium is highly dependent on the original deep earth mantle source of the magma and the specific tectonic setting. It gives you the deep source signature.
Okay, so potassium tells us where the magma was born. What does silica tell us?
Silica reflects the extent of magma fractionation.
Fractionation.
Yeah, fractionation is just the process we described, the magma cooling and minerals dropping out of the liquid. The longer a body of magma sits in its shallow chamber before erupting, the more it cools.
And the more those non-silica minerals crystallize and fall to the bottom.
Right, which means the more concentrated the remaining liquid becomes in silica.
Oh, I see. It's like taking a giant pot of soup stock and letting it simmer on the stove for days. The longer it sits and reduces, the more concentrated and thick the remaining liquid becomes.
That is a fantastic way to visualize it.
So silica tells us how long the magma aged in its shallow chamber before the volcano actually blew.
Yes. So by plotting the deep source signature, the potassium, against the shallow evolution signature, the silica, you get a highly specific two-dimensional coordinate. It acts as an elemental fingerprint.
And when researchers finally took the data from the Eruption tephra in Siberia and plotted its silica-potassium coordinates, what do they see?
It was an absolute undeniable match. When you plot silica and potassium together, the tephra occupies a very specific tight cluster on the graph. It perfectly distinguishes it from other massive Kamchatkan volcanoes that were erupting around the exact same time, like Ksudak or Shiveluch, which have totally different chemical signatures.
So there was no doubt.
None. The barcode from the ash in the remote Siberian lake perfectly matched the barcode from the caldera in Kamchatka. The Eruption tephra was, without a doubt, the Kuril Lake fallout.
That is just incredible. We've forensically linked the crime scene in Kamchatka to the microscopic evidence in Siberia. But knowing they are the same ash just raises an entirely new, honestly terrifying logistical problem.
How it got there.
Exactly. 1,700 kilometers is roughly the distance from New York City to Miami. How does a volcano throw a layer of ash that far and still form a distinct, measurable layer at the bottom of a lake? The dispersal area detailed in the sources covers more than 3 million square kilometers.
So massive.
That is a substantial portion of the entire northern hemisphere.
Right. And delivering that volume of material over that distance requires more than just a tall eruption column. It requires a massive, sustained delivery mechanism. The data maps out the ash trajectory as this enormous 500-kilometer wide path heading northwest and north-northwest, crossing the Sea of Okhotsk and pushing deep into mainland Asia.
And the sources highlight something really fascinating here. The distal tephra, which is, the geological term for the ash found extremely far away, wasn't just falling from that vertical Plinian cloud we talked about earlier.
No, it wasn't.
It was heavily composed of what volcanologists call co-ignimbrite ash. We need to talk about the mechanics of this because it sounds apocalyptic.
It truly is. This is where the interaction between the volcano's output and the surrounding geography becomes absolutely critical. Remember that Phase 3 ignimbrite?
The 50-kilometer-long avalanche of boiling rock, ash, and gas that poured out of the collapsing caldera.
Yes, that's the one. Kamchatka is a peninsula. When those massive, superheated 800-degree flows reached the coastlines, they didn't just stop. They violently slammed into the freezing waters of the Sea of Okhotsk and the Pacific Ocean.
So you have an avalanche of liquid fire hitting a freezing ocean. The thermal shock must be incredible.
It's thermal shock on a planetary scale. The rapid cooling and instantaneous steam generation caused secondary massive explosions right there on the coast, dozens of kilometers away from the actual volcano.
Oh my God.
This boiling, explosive interaction between the pyroclastic flow and the ocean water shattered the hot pumice even further. It created secondary massive plumes of ultrafine vitric, meaning glassy ash, that literally billowed up from the surface of the sea.
If I'm picturing this, imagine you have a scorching hot cast iron pan right off a high heat stove and you drop it into a sink full of cold water. You get that violent hissing explosion of steam that billows up in your face instantly.
It's a perfect visual.
Except in this case, the cast iron pan is 50 kilometers long, hundreds of meters deep, and moving at 100 kilometers an hour. The resulting steam and glass cloud would be utterly massive.
Immense. And crucially, because this secondary explosion creates such incredibly fine, lightweight dust, these co-ignimbrite plumes were easily caught by the high-altitude upper atmospheric winds.
That's a two-pronged attack.
It's a dual delivery system.
Yeah.
You have the primary stratospheric Plinian column injecting ash high into the atmosphere directly over the volcano, and simultaneously you have these secondary boiling coastal co-ignimbrite clouds pumping millions of tons of microscopic glass shards into the prevailing wind currents.
It's a terrifyingly efficient way to distribute material across a continent.
And that efficiency is exactly what allowed the tephra to become such a crucial chronostratigraphic marker for researchers today.
A chronostratigraphic marker.
Yeah.
Basically a geological bookmark, right?
Exactly. Because this ash blanketed such a vast area, 3 million square kilometers, so quickly, it left a simultaneous, identical timestamp across wildly different environments.
Right, because it all fell over a span of weeks or months.
Right. Researchers find the exact same chemical barcode in deep marine cores in the sea, in lake beds in Siberia, and in terrestrial paleosols, which are ancient buried soils across the Asian continent. If you find this ash layer, you know exactly what year you are looking at in the dirt.
Which naturally forces us to look at the atmosphere. An eruption of this magnitude, with a dual delivery ash system covering millions of square kilometers, doesn't just block the sun with physical dirt.
No, there's a huge chemical component.
Right. It injects unimaginable amounts of volatile volcanic gas directly into the stratosphere. What does injecting that much chemistry into the sky actually do to the global climate?
The volatile gas release from the K.O. eruption is almost difficult to quantify because the numbers are so absurdly large.
How do they even measure that?
Volcanologists use melt inclusions. Those are tiny bubbles of original, unerupted magma that get trapped inside hardy crystals, like quartz, before the eruption happens. They act as time capsules to calculate how much gas was originally in the magma before it depressurized.
Oh, that's clever. Based on those calculations, we are looking at an estimated 3.7 to 4.2 billion metric tons of water vapor violently injected into the atmosphere.
4 billion tons of water. That alone is staggering.
It is. Along with 43 to 49 million tons of chlorine, 8.6 to 9.8 million tons of fluorine, and most importantly for the Earth's climate system, 26 to 29 million tons of sulfur.
Sulfur is the real climate wildcard here. And the sources show that we actually have physical, tangible proof of this gas reaching the other side of the world, far beyond the physical ash fallout.
We do.
There are two distinct sulfate spikes found deep within the GISP2 ice core in Greenland, dating to around 6470 and 6476 BCE, and these spikes are strongly linked to this Kuril Lake K.O. eruption. Let's explain the ice core connection, because how does gas from Kamchatka end up buried in Greenland?
Well, ice cores act like atmospheric time capsules.
Yeah.
In places like Greenland or Antarctica, snow falls year after year, but it never fully melts. It just compresses into ice, trapping tiny bubbles of the atmosphere and atmospheric chemistry from the exact year it fell.
Right. When sulfur dioxide from a massive eruption reaches the stratosphere, it reacts with water vapor to convert into sulfuric acid aerosols.
Microscopic droplets of acid suspended in the upper atmosphere.
Yes. These aerosols are highly reflective. They spread across the hemisphere via stratospheric winds. Eventually, they slowly settle out of the atmosphere, falling with snow onto places like the Greenland ice sheet, where they are trapped forever as a concentrated layer of sulfate.
Got it.
But before they fall out, while they're suspended in the stratosphere, they bounce incoming solar radiation back into space. The sun's energy hits the aerosol blanket and reflects away, which causes a net loss of energy at the Earth's surface.
Which leads to cooling.
Exactly. This leads to short-term, but potentially severe global or hemispheric cooling.
Okay, but hold on. I want to push back on this a little bit. If we're talking about 29 million tons of sulfur, and we're finding physical acid layers in Greenland ice.
Yeah.
We're talking about a global ice age, right? Whenever people read articles about a Tambora-sized eruption throwing billions of tons of gas into the air, the immediate jump is to scream about a global apocalyptic volcanic winter.
Right, the Hollywood disaster movie scenario.
Exactly, like the whole planet freezing over, crops failing globally, massive die-offs. Does the actual scientific data from the K.O. eruption support that kind of planetary deep freeze?
It's a vital question, and it requires us to maintain a rigorous, neutral analysis of the data, stepping back from the sensationalism.
Because it's so easy to hype it up.
It really is. Now, if we look at the raw numbers, yes, the sulfur volume released by Kuril Lake is absolutely comparable to Tambora in 1815, or the massive Huayna Putina eruption in Peru in 1600. And yes, it undoubtedly caused measurable, rapid short-term cooling.
But I'm sensing a massive caveat.
The caveat is that atmospheric dynamics are incredibly complex, and equating sulfur volume directly to a volcanic winter is currently speculative. Researchers are still actively refining the precise climatic footprint of the K.O. eruption.
It's not a simple one-to-one equation.
Far from it. How these aerosols disperse depends heavily on the time of year the eruption occurred, the state of the polar vortex, and how the aerosols interact with existing climate systems like the El Niño Southern Oscillation.
So 30 million tons of sulfur doesn't guarantee a frozen planet.
It guarantees a severe climate anomaly, but not necessarily a Hollywood apocalypse. We know it cooled the region dramatically, perhaps dropping hemispheric temperatures by a degree or two for a few years, but it shouldn't be overhyped into an ice age scenario.
Right.
The data simply doesn't support the idea that the K.O. eruption caused a catastrophic global collapse of the biosphere. Science requires precision, and while the climate impact was profound, the Earth's systems are surprisingly robust.
That makes total sense. We don't need to invent an apocalypse when the reality of the data is fascinating enough on its own. Because while the global climate impacts require this nuanced, careful reading, the impact on the ground in the Northern Hemisphere, the immediate proximal reality was undeniable devastation.
Absolutely brutal.
And what follows that devastation is perhaps the most surprising part of this entire story. A bizarre, silica-fueled rebirth.
The on-the-ground reality for hundreds of kilometers around Kamchatka was a localized, absolute apocalypse. If we look at the archaeological data, the impact on human populations is stark. Researchers dug test pits on Shumshu Island in the northern Kurils, which is located about 100 kilometers south of the caldera.
100 kilometers is nothing for an eruption of this scale. Shumshu Island would have been ground zero for the ash fallout. What did the archaeologists find?
They found a complete, undeniable cultural hiatus, total erasure.
Who were the people living there before the eruption?
The artifacts belonged to the Jomon culture.
Ah, the Jomon.
Yes. The Jomon were early, highly adapted hunter-gatherers who inhabited the Japanese archipelago and expanded up into the Kuril Islands. They are famous for creating some of the earliest pottery in human history, these deeply textured vessels used for cooking and storage.
Right, they had a really sophisticated relationship with the sea, didn't they?
Very. They were skilled fishers and foragers, highly attuned to the coastal ecosystem.
And the test pits show their complete disappearance. The sources say the archaeologists found intact Jomon cultural layers, which include, charcoal from their hearths, lithic stone microblades used for tools, and red ochre used for pigments or rituals.
Yes.
But these vibrant signs of life are found sitting directly on top of the KO tephra layer. When they dig beneath the sterile volcanic glass below the KO ash, they find absolutely nothing.
The stratigraphy tells a grim story. The eruption made that entire landscape utterly uninhabitable in an instant.
You just wiped them out.
The immense ashfall would have smothered vegetation, poisoned freshwater sources with fluorine and chlorine, and choked out marine life in the shallows. The existing Jomon populations were either completely erased by the event or forced to permanently abandon the islands.
You just have this thick, sterile layer of toxic volcanic glass acting as a physical barrier in time. And then eventually, generations or centuries later, humans slowly migrate back and build their hearths directly on top of the ruins of the old world.
Exactly. The initial eruption completely sterilized the landscape. It left behind a highly acidic, lifeless, toxic lake inside the new caldera, surrounded by meters of sterile, nutrient-poor ash. It was a moonscape.
But the Earth rarely stays sterile for long, does it? Life is incredibly stubborn.
It is remarkably resilient. While the landscape was devastated, in favorable spots where the wind or rain washed the ash away quickly, pioneer plant species began to take hold. Specifically, the alderbush, Alanus verticosa, managed to survive in small pockets and quickly began resettling the barren terrain.
Alders are nitrogen fixers, right? They
Right.
pull nitrogen from the air and put it into the soil, which basically kickstarts the biological engine.
Exactly right. Their aggressive root systems began breaking down the volcanic rock, stabilizing the slopes, and starting the agonizingly slow process of soil formation. They literally paved the way for the ecosystem to return.
Which brings us to the modern Kuril Lake ecosystem. And this is, without a doubt, my absolute favorite part of this entire deep dive.
It's a great twist.
It really is. If you visit Kuril Lake today, it is not a toxic moonscape. It is pristine. The sources describe it as a deep, oligotrophic, demictic basin. Let's translate those terms because they are crucial to understanding why this lake is so special today. What makes a lake oligotrophic?
Oligotrophic essentially means the lake is relatively low in plant nutrients like phosphorus and nitrogen, but highly oxygenated. Because it lacks a massive overgrowth of algae or weeds, the water is incredibly clear and cold.
Okay, and demictic.
Demictic refers to how the water in the lake circulates. Twice a year, in the spring and the fall, the temperature shifts cause the water to literally turn over. The surface water sinks and the bottom water rises, completely mixing the lake from top to bottom.
Like stirring a massive pot of water.
Yes. This twice-a-year mixing distributes vital oxygen all the way down to the deep basin and brings whatever trace minerals are at the bottom up to the surface.
So you have a deep, crystal clear, highly oxygenated lake that actively stirs itself twice a year. And the result of these specific conditions is just astounding. Today, Kuril Lake is the largest spawning ground for sockeye salmon in all of Eurasia.
The numbers defy belief. Between 10 and 20 million sockeye salmon return from the Pacific Ocean to this specific volcanic lake every single year to spawn and die.
20 million fish.
And that massive, localized influx of marine protein supports Russia's highest concentration of brown bears.
It's a literal wildlife documentary paradise. You have millions of silver and red fish churning the waters and hundreds of massive brown bears lining the shores to feast. But here's the massive twist that ties this entire deep dive together. This biological paradise is built entirely, fundamentally, on the bones of the geological catastrophe.
It is.
There is this fascinating paradox. that the modern ecosystem relies completely on the violent volcanic past.
It all comes down to the microscopic foundation of the food web and the chemical regulation of the lake. The dominant species of phytoplankton in Kuril Lake, the microscopic algae that the zooplankton eat, which the juvenile salmon then eat, is a specific diatom called Holocene subarctica.
Diatoms are fascinating because they don't build their cell walls out of cellulose like normal plants, right? They build their shells out of glass, out of pure silica.
They do. They require massive amounts of dissolved silica in the water to survive and bloom. And if we remember the geochemical fingerprinting from earlier, what is the primary component of the rhyolitic tephra? Precisely. The massive deposits of volcanic pumice surrounding the lake, created by that catastrophic ignimbrite flow 8,500 years ago, are still there. The progressive natural erosion of this pumice catchment area acts as a constant, slow-release geological fertilizer.
Oh, wow.
Rain and snowmelt constantly wash over the volcanic rock, dissolving trace amounts of silica and carrying it down into the lake.
And because the lake is dimictic, turning over twice a year, that dissolved silica gets perfectly mixed throughout the entire water column, feeding the diatoms everywhere.
Yes.
The violent geology of the past is actively, continuously feeding the biology of the present.
It is a closed, perfect loop. The volcano supplies the silica builds the diatoms feed the zooplankton feed the millions of juvenile sockeye salmon, and the salmon feed the bears. If the VEI-7 eruption hadn't occurred, if it hadn't blanketed the region in millions of tons of silica-rich glass, this world-class fishery simply would not exist.
It means the volcano was simultaneously a weapon of mass destruction that completely erased the Jomon culture and sterilized a hemisphere's worth of landscape, and the architect of a world-class ecological nursery. It essentially built a giant 8,000-year slow-release fertilizer system for millions of salmon.
It perfectly highlights the incredible resilience of high-latitude ecosystems. The precise chemical regulation of the lake today, the very reason the salmon run is so robust, is a direct, lingering echo of the extreme violence from 8,500 years ago. It shows that in geology, destruction and creation are often the exact same process, just separated by time.
Let's take a breath and recap this immense journey.
We've covered a lot of ground.
We really have. We started with a catastrophic VEI-7 explosion that literally ripped open the southern Kamchatka Peninsula, boiling lakes and paving river valleys with liquid fire. We traveled with the ash 1,700 kilometers northwest to see the painstaking, freezing fieldwork of paleobotanists solving the mystery of the Eruption tephra by finding a single, perfectly preserved larch twig.
A true needle in a haystack.
We explored the high-tech forensic science, using electron beams to match microscopic glass shards based on the slow cooling of ancient magma chambers. We looked at the sheer atmospheric power required to dump millions of tons of sulfur into Greenland ice, pushing back on the myths of a permanent volcanic winter while acknowledging the absolute, undeniable erasure of early human settlements in the Kuril Islands.
Right.
And finally, we witnessed the birth of a thriving, silica-fueled salmon ecosystem rising directly from the toxic ashes.
If there is a central, grounded takeaway from the Kuril Lake KO eruption, it is that this event serves as an absolute masterclass in understanding Holocene volcanism. It proves that by using rigorous tephrochronology, by looking closely at the data and avoiding the trap of hyperbole, we can track the exact physical and chemical fingerprints of ancient cataclysms. The Earth maintains an incredibly detailed ledger, and it reminds us that research is always ongoing. We are still continually refining our understanding of true climatic impacts, but the localized power of these geologic events to completely wipe the slate clean and eventually foster vibrant new life is just undeniable.
The Earth keeps the receipts. It writes its history not in ink, but in the language of chemistry, ice, and stone. It really makes you wonder as you go about your day, as you look at a tranquil lake or a quiet mountain, what other unmapped, world-altering cataclysms are hidden in the dirt right beneath our feet? What other erased worlds are just waiting for the right person to look closely at a microscopic shard of glass? We started by talking about a ghost, an event with no written record. But the ghost is everywhere, holding up the very ecosystem itself. Thank you so much for joining us on this deep dive.